Okay, so this week we're looking at the handout for week 8. Question 1 is just you grind it out, right? It's, hey, you're working in A4, which we know has 12 elements, right? Exactly half the number of S4. And unfortunately, you just got to work it out. I don't think there's anything kind of interesting happening here. If anything, go just put it into Wolfram Alpha if you really need to. But yeah, I don't think that one's necessarily worth working out. 2 we can do, 3 we can do, and 4 we can do. I think those ones are at least a little bit more interesting. Are there any preferences in terms of like what gets covered first? Just because we might not be able to do them all. No preferences? Okay. Well, why don't we start off then? Let's see. I think problem 2 is a good starter. Why don't we start with problem 2? Right? And it says H and K are subgroups of G. I show that if you intersect these cosets, then that's the same thing as taking the subgroup generated by H intersect K and taking that coset, right? So let's work on this. This one's a pretty quick one, all right? So I'm only going to give you like, I don't know, 3 minutes or so. So let's spend about 3 minutes, see how much of that you can get done, and then we'll take it up in a second. Remember, do double subset inclusion, but it's almost clear enough that you could almost get away with it in a single kind of like a series of if and only ifs, but you know, if in doubt, do a double subset inclusion and see what happens. Okay, so let's take 3 minutes and see where we get with that. I'll just pause the recording.
We can't hear you, Tyler.
Man, I'm just off my game today, right? Thank you, Justin. So it's very much kind of like a set theoretic question. It feels very Math 102-ish in the sense that like we almost don't use any group theoretic properties whatsoever beyond knowing what exactly a coset actually is, right? So again, let's do double subset inclusion. So let's prove that this direction is true. So let's say, you know, we're going to choose an element in the left-hand side and show it's in the right-hand side. So we'll say let X be in the intersection. I actually think neither direction is terrible, but I think this one's just a little bit more clunky. So X is in the intersection of these two sets. So in particular, it's in both. GH and X is in GK. Okay, so since X is in GH, there exists an H in H such that X is equal to GH like that, right? Okay, but X is also in GK. And so that means GH is in GK, which in turn implies that H is in K, right? So what have we done? We've said, so X can be written as GH, where H is in both H and H is in K. Thus, H is in H intersect K. And that tells us that X is in G, H intersect K like that, right? So that gives us the first subset direction. I think the other direction is easier. In some sense, it's trivial, right? So you say, let X be in G times H intersect K. So there exists, we need to give it a different name. Let's maybe call it Y. So there exists some element in H intersect K such that X is equal to GY, right? But by definition, Y is an H. Implies that X equals GY is in GH. And since y is also in k, then x equals gy is in gk. So now we've shown that x is in both gh and gk. And therefore, it's in the intersection, right? And that completes the other direction. So I don't think we did anything like crazy tricky here in order to make these two things work out. It's a little bit weird. I can't immediately, and obviously the proof is identical for right cosets, right? I'm trying to think of an instance in which this actually happens where we're kind of like mixing these different cosets. I can't think of anything off the top of my head. It could just be that it's been a while. But yeah, I don't think this actually ends up happening too often, but this is this sort of nice thing that occurs, right? That intersections play nicely. And again, maybe that's not too crazy because we know that intersections generally play nicely with groups and subgroups, unlike unions, right? Unions are a mess. We don't generally deal with unions. Okay, so we can do problem 3 next. Problem 3 is really, really nice. So we're saying that G is basically a cyclic subgroup of order, or a cyclic group of order 25. Right, find the cosets of A5, a to the power 5. So find the, let's just do left. No, yeah, let's just do left. I mean, it doesn't actually matter because it's abelian. Okay, and if you look at what I did, pretty much the first example of cosets that we did on Monday, it's almost exactly the same question, right? It's a little bit different, but it's almost exactly the same. So give that a shot. Again, this one shouldn't take too long, but I'd recommend just even writing them out. Like if you're having a little bit of trouble figuring out where it is to begin, think about what H is, right? Like actually we can just write H down explicitly too while we're here, right? So this is like 1, a to the 5, a to the 10, a to the 15, a to the 20, like that, right? That's the cyclic subgroup generated by a to the power 5. And you can just start writing down what elements are, right? Look at the coset generated by A, look at the coset generated by A squared, and so on and so forth. And that's all you have to do because you know the group is cyclic. So every element can be written as a product of A's, right? So let's do, yeah, probably like 3 or 4 minutes for this one as well and see where we get to it. But yeah, this one shouldn't take too long. You'll very quickly, I think, see a pattern. Okay, so hopefully you've had a chance to try that out. Again, the fact that this group is cyclic makes this question much more manageable, much more approachable. First, certainly it's abelian, right? Which means left, right cosets are the same. But importantly, every single element of G looks like a to the n for some n. So effectively, if you're, like I said, if you're having trouble sort of seeing what you're supposed to do, just start multiplying or taking cosets that are powers of A, right? So take AH, A squared H, A cubed H. And if you do that, what do you get? Right? So if we take AH, that's going to be, so let's just multiply all these elements by A. And I mean, something, you know, that's not too hard to compute, right? We know how exponents work. And if we just keep doing this, you know, it's going to take a second for me to write them all out. A17, A22. But eventually what you're going to get is after a to the power of, I mean, there's obviously H itself, right? Like I didn't write that out, but that's the identity coset. But eventually you're going to notice that they start to repeat, right? So this will be the last one. A to the 4, a to the 9, A14, A19, and A to the 24, okay? Now, if you wanted to keep on going, you could, but notice that the next one is the identity coset, right? If you multiply A in, you would get A to the 5, A to the 10, A to the 14, or A to the 15, A to the 20, A to the 25. But A to the 25 is 1, right? Because that's just, you're in a group of order 25, or in particular, you're told that A has order 25. And so that becomes the identity coset again. This is all of them. These are all 5, right? After this point, the cosets repeat. And in fact, I mentioned the other day that, basically the cosets form a partition of our set. So in some sense, we can stop once we've exhausted, and once we have every element of G, we're done. And, it's going to take a little bit of inspection to realize it. But if you take a look at what we've done here, we've written out every single possible element of G, right? We have 1, A squared, A cubed. You kind of have to read down the rows. Maybe I can actually make that a little bit more clear. So if I take this thing here and maybe write it so it's like this. Okay, so now if you read down a row, you'll realize, yeah, okay, we did every single element, right? You kind of do this, and then you go like this. And as you do this, you realize, yeah, we've already written down every single element of G. And so by one of the propositions of cosets that we had before, A to the 5H will necessarily have an element of G which has already appeared in this list, and therefore must be one of these cosets, right? That was one of the things we proved the other day. 2 cosets are always have total intersection. They either are the same coset or they intersect in the empty set, right? So they have no elements in common. So they're either the same or they have no elements in common. We've written down every single element of the group already. So whatever A to the 5H must have an element which is one of these and therefore is one of these, right? So you can make that sort of argument if you want, but I think it's pretty clear here that we can just say, yeah, that's everything, right? We've written everything down. So these are the only 5 cosets. Okay, so quick quiz. This fact that I used, which is saying I've already written down every element of the group. And so if I write down A to the 5H, one of the elements of the group must already show up. What is that called? I know you all know the answer, but right, I've got 5 cosets here. Each of them have 5 elements in it. So there's 25 spaces. Once I've written down A to the 5H, I'm now writing down the 26th, 27th, 28th, 29th, and 30th element. And I know that there has to have been a repetition somewhere. What is that called? When I have 30 things and I have 25 spots, so I know that one hole has at least 2 things in it. Yeah, exactly. Pigeonhole principle, right? So if you write down, right, you can even just argue this on the pigeonhole principle. The moment you write down 6 cosets, you've already written, one of them had to have repeated, right? Because I have only 25 elements of the group, and I've got, if I have 6 cosets, each with 5 elements, that's 30 elements. So 2 of them must have had an element in common, and the moment 2 cosets have an element in common, they are the same coset, right? We learned that on Monday. If 2 cosets have the same thing in common, they are the same coset. Okay, so you can kind of pigeonhole that too, which is nice. So you can say there are at most 5, and now I've written down 5 and they are distinct. And so that has to be all of them, right? So that's a nice proof, actually. If you want to kind of say that's all of them, you say there's most 5 by the pigeonhole principle, and here are 5. So there are at least 5, and you're done. Now, problem 4, I think is the hardest. That being said, it's not too bad if you know how to approach it. So we've got H and K are subgroups. And now here's the weird thing, right? So we're going to say, show that if AH equals BK, then H equals K. Now, the reason why this is weird is we don't normally do this, right? We don't normally talk about a coset of H being equal to a coset of K, right? That's not something that we've done so far. So our usual approach and our usual technique to this isn't necessarily going to work. I do want to give you a little bit of a hint. because I think, some of you might be able to get this immediately, but if you don't get it immediately, that's okay. So hint, convince yourself that it suffices to show that AH is equal to AK. Okay, so basically what my hint here is, first of all, prove that if AH equals AK, then H equals K, right? So that's a simpler version of this problem, right? It's a special case because in this problem, the original problem, we have that AH is equal to BK. So A and B aren't necessarily the same element here, right? They're different elements. So I'm saying first prove a special case. Prove that if A and B are actually the same element, and we have AH is equal to AK, then H is equal to K. And then just try and prove this special case, right? Like try and prove that if AH equals BK, then actually AH equals AK. Okay, so that's my hint for that. I'm going to give you 5-6 minutes to try this one because I do think it is a little bit trickier. But hopefully that hint goes a long way because I think that hint will make life much, much easier than just trying to do it from scratch. Alternatively, ignore the hint completely and just do it if you think you can. Okay, so let's try this one for 6 minutes and let's see where that goes. See if you can get that one. All right. Did anyone make it? Anyone get it? Or did it even better if you managed to prove it differently than I did? I will not be upset. I promise. Sort of. Did you do it the suggested way? Yes? Not a lot of confidence. That's okay. Okay, so let's first let's convince ourselves that what I've said is true, right? So if AH equals AK, then H equals K. So let's start with that. So suppose that AH equals AK. And I mean, this one's kind of just like, in some sense, there's almost not much to say. Like every element in AH is A times something in H, every element in K is A times something in K. There obviously has to be this perfect correspondence, but I mean, like we can go through the motions and do it, which is to say, let little h be an element of H. Let's show that this element is also in K, right? So little h is in H, so that a little h is in a big H, and that is equal to AK by assumption. So that means there must exist some K. All right, so thus there exists some K. Oops. Such that AH equals AK, but now that implies H is equal to K, right? Because we can just multiply both sides by A inverse. And so this is one of those things where I was saying, like, in some sense, it's obvious that the elements in H perfectly have to correspond to K. And this is now what we wanted to do, right? So H is equal to K, which is an element of K. So H is certainly in K. So we conclude H is a subset of K. And then the relationship between these two groups is perfectly symmetric. So obviously K must also be a subset of H, right? The same argument. Shows that K is equal to, or is K, let's say K is a subset of H, right? So you do exactly the same argument. You just, everywhere there was a K and an H, you switch them around. And this gives you equality. So K is equal to H, okay? So this will work. If we end up getting that AH is equal to AK, then we're done, right? So this should be our goal. So now let's prove that that's true, right? So now suppose that AH is equal to BK, and let's show that that means that AH equals AK. All right. And the trick to this is, well, A is certainly in AH. Because it's A times the identity, right? And AH is equal to AK. So in particular, this means that there exists some element of K such that A is equal to A. Is this what I want? Oh, sorry, BK. Sorry, that's BK. So this means there exists some element K such that A is equal to BK, right? So there exists some element K such that A is equal to BK, right? Okay, so, well, what does that tell us then? Let me see, what do I want to say here? So note that, oh, here, let me just check what I said here. Yeah, apply the inverse of A, yes, depends what you mean. So let me just double check here. So I want to basically argue now that A times K is equal to A times H. Now I already have, okay, now what did I want to do here? A equals AH equals BK, so A is equal to BK for some K. Thus AK equals BK equals AH, right? Because then you get A, B inverses in K, sure. And then what? So that means then that the coset generated by, so if A inverse B is in K, that tells you that AK is equal to BK. Oh, right. Okay, yeah, sure. Yeah, let's do that. Okay. Yeah, I was going to do something a little bit different, but this is fine. So then thus A inverse B is equal to what? K inverse, I think, right? So if we do A inverse B, and then I put that on the other side, that's K inverse, which is in K. So that says that AK is equal to BK, right? Is that what you wanted to do? And then we know that BK is equal to AH. Right? And then that's what you wanted to show, that these two things are equal, and now you're done. What do you mean, oh, that's clever? That was your idea.
No, but like mine was way
Did
more
you call yourself clever?
complicated.
Is that what you were just doing?
No. Mine was like, I was like, okay, so you get like A inverse B has to be in K, right? So then because that's K inverse, then you get like A
like,
times
yeah, I assume that's
A
not what you were doing.
inverse.
But yeah, right. So then we're done because we've shown that AH is equal to AK.
Yeah, this is way more clever.
I think we might be able to go there a little bit faster. But let me see what I wrote down when I wrote this. No, I just wrote that AK was then equal to BK. But I feel like I was able to do it without doing the A inverse B part. So A is in BK. Oh, you know what we can do? We can almost immediately, no, you're right. I think this is probably a nicer way of doing it. Yeah, I like this way better. Because it directly uses one of these properties of the, it directly uses one of these properties of the cosets that we had earlier, which is nice, right? Because like, why do more work when we can just appeal to this? So yeah, so now we've proven that AK is equal to AH, and so we're done. Okay, so are there any questions about that? Does that make sense? I think it helps to know that there's this like special case that you're trying to get to. And so if you can get to AH equals AK, it's a little bit easier to do. Okay, but any questions? Everyone's okay? Oh, we're out of time anyway. So hey, that worked out perfect. Even with me showing up a little bit late. Okay, well, if there are any questions, I will hang around just because I was a little bit late. So I'm more than happy to just hang out for a bit and make sure any questions that I would have answered at the beginning of the class are resolved. If not, though, that's going to take care of us today. So for those of you who are going to take off, thank you. And yeah, thank you especially for your patience. And have a good weekend. I'll see you on Monday. Thank you. See you later.
Can I ask you a question, Tyler?
Okay, Talha, Paula, anything? Otherwise, I'm gonna go.
Can I ask you a question? Oh, I don't think you heard me. Can you hear me?
No, I can't. I can't hear anything. Is that me? Tala, can you hear her or is it just me? Oh, it's just me, so you could hear. What is going on? Okay, let's try this again. Try it now, Paula. For some reason, when I joined Zoom, it wasn't using my stuff.
Can you hear me now? No?
Oh, what is going on? It's not letting me change my speaker. What is going on? Okay, so obviously it's me, right? Okay, hold on. Let me unplug my. Okay, so first of all, you can still hear me, right? Okay. Yeah, so I am trying to change my sound output, but it's just not like Zoom is not accepting it. Okay, try speaking now, Paula. This might work.
Okay, can you hear me now?
Yes, now I can hear you.
Yay. Okay, I'm confused by my own name. Well, no, I'm just can you explain like the last line again? Like how did you go from like, okay, so A inverse B is equal to K inverse, which is in K. So then we're done.
Right. Okay. So the notion of cosets is precisely that AH equals BH if and only if A inverse B is in H. So that's something you can either just prove directly, or based off of what I did in the last video, I proved that basically if you define an equivalence relation where you say that A is similar to B, if this is true, then these are the equivalence classes under that equivalence relation.
Oh, okay.
Yeah. So once we have that A inverse B is in K, that tells us that they have the same equivalence classes and therefore that they have the same coset. So AK is equal to BK, but then we knew that BK was equal to AH to start with.
Oh, okay. That makes sense then. Thank you. That was my question.
Okay, no problem. Tala, anything from you now that I can hear? Okay, no problem, everyone. See you both. Yeah, sounds good. Ciao.